Ken? Ouais, vas-y, Ken.
Okay, so a few people ask us how we did this challenge, how we made it. So let's reverse how we are doing, or we are making a reverse challenge. Okay, so it begins with a IRC message, which is fully translated and edited. Which is basically say, hey, do you have time for a challenge? To make a challenge in just a few days and test it, and it has to be the final challenge from random memories. So it has to be at least a little difficult. So yeah, we have time. Work at the CA. So the guidelines, there was that we have to do a reverse challenge. This is the last step, so it has to be not tedious but challenging, and we want it to don't have any guess in it. So the idea was to force people to use tools because the tools are the future, at least we hope. So the goal was to focus on automation and not on efficient manual analysis and expert and experience analysis. So we have also to prevent trivial attacks. And MyAsm should not be the only viable solution. That was a tough one. And there should be some hype at the end. So that was the worst part. So the implementation is a lot of binary. So let's say lit for architectures to OS, and we just done a few of ARM, and I will explain why later. Each binary is a different equation to solve, and there are all their own packer, and the validator is an unnecessary concurrent Rust source code. So the inspiration come from T0 DevCon challenge, which is actually I think it's 100 different challenge, but here is the solution, which is only based on objdump, grep, and XXD. So we don't want this, okay? Maybe it's solvable with this kind of tricks, but we hope it's not. So we have to first produce the equations. So how to do that? The first approach is the smart way. We have to produce a function in a Galois field computation with only one and only one value, such that the result, so that you can obtain a zero. We have to apply reversible transformation to it, mix it with expand your use operation, etc., and do it several times. So the approach that we take is the lazy way. You just brute force random equations and ask that three if there is the only one answer constraint. So let's do this, and the number required time. So the implementation is basically based on MyAsm, because we are doing operation in the bit vector world. So you can use the IR MyAsm that's Adrien introduced. So we start with the input, apply random operation with random constants to produce the intermediate variables. Then we mix these variables with also random operation. Finally, we just sum all of them, took a random value, evaluate the expression, and ask Z3 for MyAsm if there is only one way to get the zero at the end. So we want an answer and only one. So if this is the case, we save the input, we save the C code. We obtain the C code by asking MyAsm to translate it to C. It's just unreadable C code, which looks like this. And we also want to avoid common attacks. So for instance, to avoid the brute force, basic brute force, the input is 64 bytes, sorry. The patterns are random to avoid the famous so-called grep attack. And we want to avoid too easy tracing. So if someone is just tracing the program from the beginning to the end, we don't want it to reach the final equation. So we just insert random checks to avoid a full equation dump in just one run. So you get these, okay, you can see it, but there is some condition here and here. You just check a bit mask, and you probably, with a random input, you probably won't be able to go through it. The other goal is that multiple tools can be used to solve this. So there is just only a few challenges on ARM architectures because a lot of tools are not supporting it yet. So they are doable by hand. It's boring, but you can do it. There is a kind of rewards for the guys who are doing it automatically. We don't have float, we don't use too exotic opcodes, no loops, and we think that this challenge is solvable with Triton, Manticore, Anger, Miasm. We actually know that some people, of course, solve it with the Miasm, but there is someone which also solve it with the Anger. There are the solution which are being presented by Adrien, which is using the symbolic execution with the state splitting. Another one which is possible and actually works is what Sébastien Bardin presents this morning, which is the dynamic symbolic execution. So you just basically going through your CFG, and when you get on a split, you're asking the solver if he's able to go to the branch that interests you, and you go on until you reach the final equation. And the final possibility is to use the dependency graph, which is actually you start from the end of the graph and you ask for every path that are possible to reach this final equation.
So for the packing part, so you saw that there was a packer in this challenge. We wanted to generate one different packer per binary, so that's 1,000 packers, so we couldn't afford to write them manually, all of them. So what we did is that when the equation was compiled, we just took the binary blob, and then we generated random packers with we had a list of inversible operation and their inverse. First we pick an operator size because we can apply this operation on 1 byte, 2 bytes, 4 bytes, or 8 bytes, which generates different shapes of code. And then we generate a list of random pairs of instructions that give at the end a packer. And in parallel, we apply the packing instruction on the original blob so that we can have loads of different packers. And yes, we generate C code because it has to compile in lots of in 4 different architecture later. Then the packer is really simple, as Adrien showed you. So it maps the code. It maps memory and packs the code, and then it calls mprotect to make it executable, and that's the right moment to break and bypass all the packer that was before. And then in the end, we clean everything up because we wanted to do something that was really clean and everything. So that it looked like when it was in C, and yeah, as I said, it was meant to be bypassed. So the simple one that you saw was just here to show you how it was built, but all the other packers were obfuscated with OLLVM, so that it was a hint for the people not to generate unpackers with static analysis. Then yeah, that's just a quick word on the whole tool chain. So there was a lot of things to do because for all different targets there was for Linux, Windows, x86, x64, ARM, AArch64. We had to compile, pack, obfuscate, so calling clang with OLLVM with cross builds, and then we tested every equation so that we are sure that it was correct. So it was quite a bit of work, but funny work. So yeah, that's basically the whole process that you saw before. We compile the equation, we extract it, we pack it, then we strip and obfuscate, then we test that it works. We do this for all the binaries, and then we have to update the validator that was described before. The things that we didn't do and we could have done to make it harder, but maybe too lengthy for this challenge, would be to add loops in the equations so that static analysis is harder to do, and that DEC has to explore lots of different states. We didn't use any anti-emulation tricks like tracing threads or things like that, nor anti-symbolic execution tricks. the thing was just to force people to do automatization. And yeah, just for the fun, we wanted to write a validation process that was way too much complicated. So the basic idea is to draw all the solutions of the equations, and it gives a key to decrypt the final flag. But we thought that it was fun to use SHA-SHA-20 because it wasn't implemented maybe everywhere. And then we thought that it was fun to hash the numbers before, and then maybe we could do that concurrently with a pool of thread, you know, to be quicker. First with the global lock on the data, then with the atomic operations. But the thing with atomic operations is that there is the thing called ordering that is almost always okay on x86, but not always okay on ARM. So we chose the right ordering, and then we tested that it was okay on ARM too with QEMU. And then we tried to make efforts not to do excessive malloc. So when we passed the file, we took care of that too. And then we thought that it was nice to use nightly features of the language. So we forced to use the nightly compiler of Rust. So either you had to download this nightly compiler or understand the code and recode it manually. And then yes, the code, the final flag wasn't only ASCII. And of course, we did this in Rust for safety and performance sakes. So thank you for this. We really enjoyed refreshing the scoreboard, and congratulations for the people that had the courage to do it fully.